So here is a summary of how you'd go about using partial fraction decomposition if you're trying to integrate a rational function where you cannot use U substitution or trigonometric substitution. So the first thing, and we haven't encountered this yet, but we'll look at an example of this in just a bit, is what to do if you have an improper fraction. And if you don't remember what an improper fraction is if you have some function f of x over g of x, it's considered improper if the degree of the numerator is greater than or equal to the degree of the denominator. So if that's the case, then you're going to want to use polynomial long division so that you can rewrite your function f of x over g of x as a quotient plus a remainder over the divisor. So if your rational function is not improper, or rather it is proper, where the degree of the numerator is less than the degree of the denominator, then you want to factor the denominator if possible. So a lot of the examples that we saw, the denominator was already factored. If it's not, you want to make sure you factor it. So I'm going to let you read over the remaining steps. You can pause the video if you'd like to read over those. So let's look at example 8. We want to find the integral of this long messy thing, and notice that this is an improper fraction because the degree of the numerator is greater than or equal to the degree of the denominator. In the numerator we have a cubic polynomial, and in the denominator we have a quadratic polynomial. So here is where we're going to need to use polynomial long division. Okay, so I've gone ahead and I've written my two polynomials, one inside the division bar and one outside. So if you don't remember how long division works, in this top position here, I'm looking for something that when I multiply it to x squared, it gives me this thing here, which is 3x cubed. So the value that I multiply to x squared to give me 3x cubed is 3x. And now what I want to do is I want to multiply 3x to each of these things here. I'm going to put a minus sign, and then I'm going to put my little parentheses here. And so 3x times x squared is 3x cubed. Then 3x times negative 2x is negative 6x squared. And then 3x times negative 3 is minus 9x. And now I want to subtract these. So 3x cubed minus 3x cubed is 0. Negative 5x squared minus negative 6x squared is just x squared. Negative 11x minus negative 9x gives me minus 2x, and then I want to bring down this 9 here. So I have plus 9. I'm going to erase this 0. Okay, so now what we want to do is in this position here next to the 3x, I'm looking for what do I multiply to x squared to give me the thing that's in this position here. And notice that those are the same things, so I'm going to put plus 1 because 1 times x squared gives me x squared, and then I still need to multiply these things together. So again, I'm going to put a minus. 1 times x squared is x squared. 1 times negative 2x is negative 2x. And then 1 times negative 3 is negative 3. I'm going to go ahead and subtract vertically. So x squared minus x squared is 0. Negative 2x minus negative 2x is also 0. And then 9 minus negative 3 is positive 12. Now, I can't go any further because now I have a constant, so that constant represents my remainder. So this 12 is my remainder, and then let me erase a little bit. This thing here on top of my division bar, that thing is my quotient, so it's 3x plus 1. So what does all of that mean? This is going to allow us to rewrite our original rational function. So when I divide the cubic polynomial by the quadratic polynomial, we get 3x plus 1, And then we have a remainder of 12, and then that gets divided by the original thing we were dividing by, which was x squared minus 2x minus 3. So now, if we want to integrate this thing, then we could integrate this thing. And on the right-hand side, I'm going to go ahead and split that up into multiple integrals. Now, I have a quadratic in the denominator, and if you'll notice, that quadratic is nicely factorable, and it factors into, let's see, x minus 3 times x plus 1 dx. And we have two integrals now. The first integral, we could just use power rule, and on the second integral, we're going to need to use partial fraction decomposition. So I've gone ahead and I've set up my equation, and I want to multiply every term in that equation by the least common multiple of all of the fractions. And so we want to multiply through by x minus 3 times x plus 1. The resulting equation will be 12 equals capital A times x plus 1 plus capital B times x minus 3. Now from here, we can plug in strategic values for x, one of them being -1. If I do that, we get 12 equals, the A is going to get eliminated, and then we'll have B times -1 minus 3. That's going to give us -4b is equal to 12, which implies that b is equal to -3. Let's go ahead and choose another strategic x value. I'm going to choose +3. That's going to tell us that 12 is equal to a times 3 plus 1 is 4. The b is going to get eliminated, and then if I divide both sides by 4, we're going to get a is equal to 3. So let's come up here and replace a and b. A is equal to 3, and b is equal to -3. I'm going to clean up the screen a bit. Alright, so let's go ahead and evaluate these integrals that we have now. So I'm going to use the power rule. We have 3x squared over 2 plus x, and then we have plus 3 times the integral of 1 over x minus 3 dx minus 3 times the integral of 1 over x plus 1 dx. And so we'll get 3x squared over 2 plus x plus 3 times the natural log of the absolute value of x minus 3 minus 3 times the natural log of the absolute value of x plus 1 plus our constant of integration. And here is our final answer.